Here's a question that sounds almost too simple to ask. How long is the coastline of Britain? You'd think you just grab a ruler and measure. But watch what happens. Use a long ruler, you get one answer. Use a shorter ruler and you catch more of the little bays and inlets, so the number goes up. Shorter still, and it climbs again. The coastline, it turns out, doesn't have a length. It just keeps getting longer, forever. This is the world of fractals. The word comes from the Latin fractus, broken, fractured. And that's the whole idea. Shapes that stay jagged at every scale. Zoom in and the roughness never smooths out. Benoit Mandelbrot, the father of the field, half-jokingly called it the theory of roughness because nature is full of it. Coastlines, mountains, clouds, the branching of your own blood vessels. The key property has a name, self-similarity. Break a fractal into pieces, and each piece is a shrunken copy of the whole. Zoom into a corner, and you see the same shape staring back at you. That single idea, a thing built out of smaller versions of itself, is the engine behind everything we're about to draw. Let's build one by hand. Start with a straight segment. Now the rule. Take the middle third, and pop it up into a little triangular tent. One segment becomes 4. Do it again to every segment. And again. Keep going forever and you get the Koch curve, a line that is nothing but corners all the way down. Now here's the first strange thing. Every step, each segment splits into 4 pieces, and each piece is 1/3 as long. So the total length gets multiplied by 4/3 every single time. For thirds, again and again without end. That product runs off to infinity. The Koch curve has infinite length. Now do the same thing starting from a triangle instead of a segment, and you get the Koch snowflake. Its edge is infinitely long, you could never trace it. And yet, the whole thing fits inside a small circle you could draw around it. Finite area, infinite perimeter. A shape you can hold in your hand with a border you could never finish walking. So how do you even measure a thing like this? The honest answer is, we need a better idea of dimension. Take an ordinary object and cut each side into k pieces. A line splits into k copies. A square into k squared. A cube into k cubed. See the pattern? The exponent is the dimension. 1, 2, 3. So let's just turn that pattern into a definition. If shrinking by a factor of k gives you n copies of the whole, then n equals k to the power d, and d is the dimension. Solve for it and you get d equals log n over log k. And here's the beautiful part. Nothing forces d to be a whole number. So plug in the Koch curve. One piece becomes 4 copies, that's n equals 4. And each is 1/3 the size, so k equals 3. That gives d equals log 4 over log 3, which is about 1.26. Not 1. Not 2. Somewhere in between, more than a line, less than a filled-in area. A dimension that isn't a whole number at all. Fractals can also go the other way below dimension 1. Meet the Cantor set. Start with a line segment and just delete the middle third. Then delete the middle third of what's left. And again. Forever. What survives is a fine dust of points. Full of holes but never quite empty. And get this. Add up everything you threw away, 1/3 plus 2/9 plus 4/27, on, and it sums to exactly 1. The whole length is gone. And yet the set that remains has as many points as the entire line you started with. Its dimension, log 2 over log 3, about 0.63, between a scatter of points and a line. Now for the crown jewel. It comes from one deceptively simple rule. Take a complex number, square it, and add a constant c. Then take that result, square it, add c again. And repeat. For some values of c, the numbers stay small and tame forever. For others, they blow up and race off to infinity. That single fork in the road is the whole story. Here's the clever test the computer uses. Watch a single point orbit. If the size ever climbs past 2, it's doomed. It can only grow from there off to infinity. But if it stays trapped inside that circle of radius 2, no matter how long you wait, then C belongs to the Mandelbrot set. Do that test for every C, color by how fast the rest escape, and this is the shape that appears, a black heart with a boundary that is fractal on every scale. Freeze C instead and vary the starting point and you get a Julia set, one for every C, infinitely many. And here's the deep link. The Julia set holds together in one piece exactly when C lives inside the Mandelbrot set. Push C outside and it shatters into a Cantor dust of isolated points. So the coastline never had a length, and roughness has its own kind of dimension. Nature, it turns out, was never smooth. It was fractal all along.